Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we will be looking at an example for chemical equilibrium. So we want to, in this case, look at how we can come up with the equations describing chemical equilibrium by looking at a specific reacting mixture. In this case, we have the reaction C2H6 in the gas phase reacts in an equilibrium reaction to make C2H4 plus H2 all in the gas phase. Now this reaction is carried out at 1 bar and 25 degrees C, and we want to find the expression for the equilibrium mixture, and then if the feed is 10 moles of C2H6 at these conditions, what would be the extent of reaction? So we need the delta G of reaction. In this particular reaction, it's going to be the Gibbs energy of formation for the hydrogen plus the ethylene C2H4 minus the ethane. Now for hydrogen, the Gibbs energy of formation will be 0 because this is the natural elemental form. For C2H4, I found 68.43 kilojoules per mole, and for the ethane, I found negative 31, let me clean that up, negative 31.86 kilojoules per mole. And so delta G of reaction is 100.29 kilojoules per mole. This tells me the value for the equilibrium constant, K sub A at 25 degrees C, will be the exponential of negative 100.29 kilojoules per mole over RT, and I just need to make sure that I use consistent units so that this cancels. Exponential or these other transcendental functions require that the argument be dimension-free. So kilojoules per mole Kelvin times temperature is 298 Kelvin, and therefore K sub A is 2.69 times 10 to the negative 18. Now, I also know that K sub A is the product of the activities to the new exponents, and if I assume that all of these are at a low enough pressure that they would be an ideal gas, then in this particular case I'm going to have Y for the hydrogen, Y for C2H4, and Y for C2H6. The hydrogen and C2H4 are products, so they have positive exponents. C2H6 has a negative 1 exponent. So this is mole fractions. I don't exactly have that, but I do know that the number of moles of each of these can be calculated in terms of extent of reaction. So in this case, I have the original number of moles of hydrogen plus X, the original number of moles of C2H4 plus X, and the original number of moles of C2H6 minus X. If I were to add these up to get a total, then that would be the total number of moles I started with, which would be just adding all those up, plus X minus X, so plus X. Therefore, I can write my K sub A in terms of Y's. Y for H2 is the original number of moles of hydrogen plus X over the total original plus X. And for the others, I'm going to do similarly. And as you see here, I've written down the Y's for each of these, and it's equal to 2.69 times 10 to the minus 18. Now, in the example, they say, what happens if you had a feed of 10 moles of C2H6? So substituting in 0 for the original amount of C2H4 and H2, and 10 for the original amount of C2H6, I end up with this expression here. I can multiply top and bottom by 10 plus x squared. And then if I multiply both sides of this equation I have by 100 minus x squared,